What's up, everyone? Today we're going to finish off the inequality that we didn't finish from Monday's video, which says that there are two rational functions. And again, rational functions means that they are in fraction form, that both numerator and denominator are just polynomials. And the reason that we didn't finish up the proof on Monday was again because we end up with a factor that is in degree 3. In other words, it is a cubic expression. But unfortunately, we could not factor out nicely in to two or more terms that are in integer coefficients. So we end up with this step here, and we couldn't continue. So what do we do? Well, in the video from yesterday and also the video from Tuesday, well, again, there's some technical issues that the video that was supposed to be published yesterday actually wasn't published, and it was finally up this morning. But anyway, if you didn't watch it, just go find out what I did in those videos. In those two videos, we found out the what's so-called the cubic formula, and in fact, we actually found all three solutions of the cubic formula, meaning that those three solutions will actually satisfy any conditions for any arbitrary cubic equation. In other words, for all the general cubic equations, ax cubed plus bx squared plus cx plus d equals 0, we can always use the cubic formula that we found from yesterday's video to actually give us all three solutions. And of course, we know that there has to be at least one real solution, and then the other two, it could be real, it could be complex, we don't know. And therefore, now we can actually move on and finish up our proof. So on the right hand side, we have all the work that we have done in the previous video, and we are making it into a side note so that it will help us to solve the cubic expression factor and help us to finish up the proof. So if you want to give it a try, you can just pause the video right now, and until you finish it, or if you want to check the answers right away, you can just move on and finish the video. Also, don't forget to like and subscribe to my channel so that you can also find out more of my other videos, and turn on the notification so that whenever I have new videos, you won't miss it either. Here we go. So in Monday's video, we actually end up with the step that we get three factors, x minus 1 times x minus 3 times the cubic expression, which is greater than or equal to 0. And again, how do we solve an inequality of polynomial? We would like to find out the what's so-called the roots if we set it equal to 0. And again, solving out the roots will help us to figure out what we need to do in our last step. So we already have two roots, x equals 1 and x equals 3. Now we need to find out the remaining three roots. And since we already have the cubic formula, we're now going to use the cubic formula to help us getting the last three roots. Here we go. So from the expression, we see that the leading coefficient a is equal to 4, b is equal to negative 13, c is equal to positive 8, and d is equal to 9. So if we look at our expression here of the cubic formula, we find out we have the expression on the right hand side that involves with a and b, of course, as well as u and v, and the letter omega here, where omega is a fixed value, which is actually known as the cube root of cube root of the unity. So the problem is we don't have u nor v yet. How should we find out the u and v? Well, if we trace back up, we know that u and v are actually in terms of q and p. And what are p and q? Well, we can just go back up one more time and see that p and q are actually in terms of the coefficients. So let's substitute it. We get p is equal to 3ac, where a is 4, c is 8, so 3 times 4 is 12, times 8 is 96, minus b squared. Well, b is negative 13, so square it, the negative sign will be gone, and we have 13 squared, which is 169, over 3a squared, where a is again 4, so square it is 16 times 3 is 48. So that will actually give us 69, and then plus 4, which is negative 73 over 48. Or I can just put the negative down here. Good. So that's our p value. For the q value, we'll do the similar thing. We're going to substitute in whatever we need to. So let's deal with the denominator first. We have 27 times a cubed, and again a is 4, so a cubed is 4 to the third power, which is 64, times 27. That is actually give us 200, no, not 216. That is actually going to give us, let me calculate it quickly. We're going to get, let's see, 1,728 in our denominator. Good. Then on top we have 27a squared d, which is again a squared is 16 times 27. That will actually give us 432 times 9, and that will be 3,888. Very nice. Then minus 9 times ABC. But since only one of the term is negative, it's going to cancel out with the minus sign and give us a plus sign. So we have 9 times A, which is 36, times BC, which is 104. Then this is going to give us 3,744. And last but not least, we have 2b cubed. And again, b is negative, so we will end up with negative sign here. Then b cubed is 13 cubed, which is 169 times 13. That is the same as, let's see, we're going to get 2,197. Then we need to multiply by 2. This gives us 4,394. So if we do our simplification on top, we actually would end up with, let's see, we actually get here is minus 650. So we have 3,238 over 1,728. And again, of course, we can just try to simplify a little bit more, which gives us 1,619 over we divide this by 2, we get 864. Now, can we simplify one more time? Unfortunately, no, because the denominator is actually is just only have the prime factors 2 and 3, and 1,619 is not divisible by 2, not divisible by 3. So that is actually the simplest form already. Good. So now we know what the P and Q value are. We just need to substitute back in to the U and V so that we'll be able to finish up our calculation of the cube of the solution of this cubic expression. So we have u is equal to, of course, we still have the cube root of negative q, which is negative 1619 over 864 plus the square root of q squared plus 4 times p squared over 27, or I can just write it this way, 4 over 27 times p cube, actually, not square. So we're going to multiply with this. And then all over 2. So, of course, we can just try to simplify a little bit and do a lot of calculations. So, what we are going to get, this is what we're going to get. Okay, so we actually get something that looks a lot nicer after we simplify it. And that's for the u value. V, we can actually do the similar thing. But recall that the product of uv, or u times v, is actually equal to negative p over 3. Negative p over 3. So we actually can use the relation v is equal to negative p over 3u. And then, instead of doing the calculation one more time, we can just take this value and put it back in here. So what are we going to get? We now get the following. Now, remember that p is actually this value. So we get negative p, which is 73 over, over 48. Divided by 3u. So again, if we put the u on, since we have the u on the bottom, those will cancel out and going to give us, let's see, we have 3 cancel with 12, so we have 4 in the denominator. So we end up with negative 73 over 48 over 1 over 4 times the remaining part in the denominator. So we actually, instead of having this part on top, we're going to get 1 over this part, the cube root. And again, you can also try to simplify it by taking the conjugates and then make this part on top and then try to make it nicer. But is it really necessary? Not really anymore, because again, later on, what we just need to do is we need the approximate value instead of just the exact value of it, because we only want to put our solutions in order. So here, if we simplify it, we get negative, we still have negative 1 over 12, because now we can just flip this 1/4 to the top, meaning that we're going to multiply this part by 4, so cancel out, and then we have a 12. And then for the 73, I'm going to put it right here, and you can check it online and or by your own hand if you want to, and see if I actually get the right result. But now we have u and v. We just need to substitute back into our equation so that we'll be able to finish up our calculation. So this is what we're going to do. Now we know that there are 3 x values for this cubic expression. So we first suppose that k is equal to 0, then we are going to use k equals 1, and finally we are going to use k equals 2 into this expression to find out the 3 different solutions. For the first solutions, when k is equal to 0, that's the best, because now we just substitute in and we can ignore the omega at the moment, so that we don't have to consider the complex part of it. And here, a quick hint is that this term inside of well, this term is actually real. So even though we might end up with negative, we have a negative value in the cube root, so we can always guarantee that this term is actually real. This term is also real. So when k is equal to 0, we can almost guarantee that we will get the like one of the real solutions. Then the problem is if we actually get two more solutions when k is equal to 1 and k is equal to 2. So anyway, now we get negative b again is negative 13 over 3a. So we have 13 over 3 times a, which is 3 times 4. That gives us 12 here, which is the first term. Plus u is here, plus v. And we know that this is actually a real number. Again, our argument is this term is real, so that this term is a real number. And even if this is a negative value, we're now taking the cube root. So if we take the cube root, we can guarantee that this is still a real number, because we can have if we take the third power of a negative value, we will end up with a negative value. So we can think it backward and say that this must exist in the real line. Good. Now for the other two, we are going to get the following. So I'll label it as x1, x2, and x3. For the other two, we will get omega times u plus v over omega. And then here we get omega squared. And again, omega squared is actually the same as 1 over omega. So I'll write as u over omega plus, and here again, if we square it, 1 over omega squared is actually the same as omega itself. So we actually get this. But the calculation there is not easy to verify, but you still can try to check it on the internet and show that it is true. But the quick answer is that these two are unfortunately not real numbers. They're actually complex, non-real complex numbers, meaning that the I term are still remaining somewhere after you try to simplify it. Therefore, for the expression up here, we actually only have one real solution, which is this one. So last thing, what is the approximate value of this real solution? Well, this is approximately equal to negative 0.5508. So we actually get a negative solution for this expression, where the other two are again positive 1 and positive 3. So what does that mean? It actually means that if we think of the other two solutions, the non-real solutions, and if we put them together, that part is always guaranteed us that those will be always positive. So in fact, we can actually get the following. We now say that we have three values. So again, we don't need three rows. We're only doing algebra, not calculus. Anyway, we have the x part and again the y part, or f of x. Then we have the three roots. Well, first we have x1, and again here I'll write with the short notation, and then we have the roots positive 1, and last but not least we have positive 3. And here are what we're going to get. Again, since these three are the roots of the polynomial from the left hand side, when we substitute these values in, we can guarantee that the term is turning into 0. So last but not least, we need to check whether we get positive or negative between the solutions. So if we think of the graph, here we actually have a degree 5 polynomial. So from the big graph, we are going to get something like this, if there are actually 5 solutions. And of course, we only have 3, so we might actually have a shift somehow, but it doesn't really matter from the graph, because the graph is only helping us to know the 2 tails or the 2 ends. That means that for the 2 ends, the left end is always giving us a negative result, where the right end is always giving us a positive result. Last but not least, we're now going to use the shortcut that we have learned from a video last week. So remember, we just said that we can also determine whether we have a sign change or not based on the roots that we pass through, and also based on the degree of the factor. In other words, we are going to consider whether the root is a simple root or a double root or whatever. So for example, x equals 3 actually is a simple root because it is in degree 1 in the factor. There's only 1 copy, and we had the conclusion that whenever the degree is odd, we always get a sign change when we pass through that point. So if we end up with positive, it means that before we pass the point, we have an opposite sign, meaning we get a negative. Similarly, x minus 1 is a simple root because it has only a degree 1. So we also have a sign change, so we end up with positive. And again, we can finally verify it with the very first solution that we have, x1. If we factor it out, we have x minus x1 times x minus x2 times x minus x3. So it means that we have only 1 copy of x minus x1, and therefore we have a sign change as well. So this is checked. So we can now finalize our solution, our conclusion. Since we want the expression or the quintic polynomial be greater than or equal to 0, we are going to find out which part are positive or 0, or in other words, which part are non-negative from the table. So first we have a negative, so we take it out. Then we are going to include the solution, of course, because we include 0. And after that, we have a positive region here, so we're going to keep it, and then we turn back down to 0. And later on, we have a negative, so we will take the negative part out. And finally, we have 0 and positive again. So our solution will be boxed in black, and numerically, this is what we're going to get. Our final solution will be x is between and equal and including the endpoints from x1 to 1, where x1 is again the expression up there, 13 over 12 plus u plus v. Again, u and v can be found in the expression on the right hand side. So because there's not enough room, I'm going to leave it in this form. You just need to substitute it and find it out. And this completes our first box. So we now need to include the second box right here, which says x is greater than or equal to 3. And that is it. This is our solution of the inequality that we had on Monday. Whew, it's pretty long. But I think it's actually cool because this one problem actually combines a lot of ideas in it, as well as some ideas that we probably haven't, well, most likely haven't learned, and perhaps we haven't even thought of when we were actually in class, in math class. So that's it. Again, if you think this is cool, well, I think it's cool to it's definitely cool to me. But if you think this is cool, please like my video. And if you have any thoughts or ideas, please leave your comment below. I'll see you guys in the next video.